Hello everyone, this is Angeline Anani from Avionics Department, and the topic given to me is from Unit 5 System Assessment, Validation and Certification. From that first topic we are going to see today evaluating system design and future architecture.
Wow!
Evaluating system design is very important in order for a design to meet high performance and high level safety. Now we are going to see some key objectives of design evaluation, which is first, safety and integrity. For a simple explanation to be given, can this system fail without crashing the plane? So what does this mean? The system must be safe to fly, since if computers can fail due to bugs, hardware errors or external events, the system must be designed to handle its own failure. The key concepts to be known is first, fault tolerance and redundancy. Having backups. If the primary computer controlling the wing flap fails, a secondary identical computer immediately takes over, which is redundancy. This prevents a failure or a fault from leading to a disaster. Next, fault detection or isolation. The system must know when a part has failed and immediately wall it off so it doesn't corrupt other systems. Moving on to the second objective, requirements compliance, doing what it's supposed to do. The design actually solve the problem it is set to solve? What it means is, before designing the system, the manufacturer defines what the airplane must do. The evaluation confirms that every piece of the new architecture can be clearly traced back to and fulfills those original needs. The goal is to avoid building a complex, beautiful and expensive system that fails to meet a crucial aircraft function, such as displaying the correct airspeed or navigating precisely. Design should be in such a way that it meets its own requirements. Moving on to the third objective, feasibility and affordability. The design should be built in such a way that it should be affordable and the components which are used should be feasible and long-lasting. Fourth objective is testability and verification. Ensure that the design is structured, verified and validated. There are other formal safety processes for system evaluation. So, safety assessment process ARP4761. This is a formal multi-step process for proving that the aircraft is safe. First, functional hazard analysis is done, which in simple terms we could say that what bad things could happen. Here they are brainstorming every possible failure for a aircraft could go through, like loss of thrust control, inaccurate altitude display and etc. And then preliminary system safety assessment is done, where here how will we prevent the bad things. So you take a list of hazards from the FHA and show how a proposed system design will handle them. And then system safety assessment. Did we build it safely? This is the final check. After the system is actually built, assessment confirms that the implemented working system successfully meets all the safety rules established in the PSSA and FHA. Till here, we can conclude the evaluation of system design. And moving on to the future architecture now. The future architecture. The shift in avionics is all about moving from a rigid system to a flexible, software-driven platform that can be easily upgraded, like moving from a landline phone system to modern smartphone apps. First, integrated modular avionics, which is IMA. In simple terms, we can say that many apps on one supercomputer. What it means, instead of having a separate computer for every function, like one for navigation, one for radio, one for display, IMA puts many different functions onto a small set of powerful standardized computing modules. This saves massive amounts of weight and wiring. But the biggest risk is that one function interfering with another. This can cause some failures. Moving on to the second one, Open Systems Architecture, OSA and FACE. Historically, once an aircraft was designed, you were locked into that one single vendor's components. In OSA, uses publicly available standards for hardware and software interfaces. FACE is a specific standard that ensures software written by any compliant vendor can plug and play into the aircraft's core architecture. Thirdly, autonomous and AI/ML systems, adding a smart brain to the cockpit, incorporating technologies that learn and make complex decisions, such as a system that monitors engine health and automatically predicts whether a part will fail, or an autopilot that handles complex real-time mission changes. The major evaluation challenges. Traditional avionics are deterministic. You test every possible input and you know the exact output. But in AI/ML, it's very non-deterministic. It learns, and sometimes the why behind its decision is very complex and hard to trace. So for this, new evaluation methods are required, which is operational envelope, defining the exact limited situations that AI is allowed to operate, and then training the data, rigorously checking the data used to train the AI to ensure it's high quality, unbiased, and covers all relevant scenarios.